Let us now find out a way to estimate the clearness index. Clearness index KT is nothing but the ratio of the daily energy incident on a horizontal flat plate collector with atmospheric effects with atmosphere 2 is divided by the daily energy incident on a horizontal flat plate collector without atmosphere. Now the key here is with and without atmosphere. Now this is equal to the daily energy incident on horizontal flat plate with atmosphere. We have been using the symbol HA, and the daily energy incident on horizontal flat plate without atmosphere, we have been using the symbol H naught. Now H naught can be computed. It is determinable by means of a closed form solution, and all this needs is input like the latitude of the locality and the day number, and then you can accurately compute it using 3D geometry with reasonably good accuracy. However, HA is the energy with atmospheric effects, and that is difficult to calculate, but we can measure it. So if we measure HA, we calculate H naught, then we get the accurate correct value of KT at any given place. So now how do we do that? How do we measure KT? First, what we do is take a pyrometer and place the pyrometer at the place of interest. Now what is a pyrometer? Pyrometer is an instrument that can measure insolation. So it is used in all solar based experiments, and it is based on thermal principles. It has a thermopile, and by means of the Seebeck effect, it converts the incident radiation to electric voltage value, and the voltage value gives us a measure of the incident insolation. Now let me show you the pyrometer, which will give you an idea of what it is, and you will understand what I mean by pyrometer. Look at this equipment. This is a pyrometer. You see that there is a glass bulb on top, and inside, let me tilt it. So inside there is a black item. Now that is a thermopile. Now the radiation falls on the thermopile and heats up the thermopile, and that becomes the hot spot. And the pyrometer body is the cold junction, and there will be a temperature gradient between the hot junction and the cold junction, and that will give a voltage output, a thermoelectric EMF based on the Seebeck effect. Now through this wire we will be able to measure what is the voltage using a multimeter. Now this thermocouple or this pyrometer can measure, so it is, let me open this out. And you will get a look at the nameplate. So you see here, nameplate indicates when it is 0 volts, the output is 0 watt per meter square, and if the output is 10 volts, the output is 2000 watt per meter square. Of course, the insolation from the sun will not exceed 1000 watt per meter square So you will get probably at most 5 volts from these terminals. Now if you look at the side here, you see this green green spot here. That is nothing but a spirit level type of an item which is there, mechanism, which will do the job of positioning the pyrometer horizontally. You can position it horizontally at a place and then allow it to measure the radiation, and it will give you the output in voltage, which is a direct measure of the insolation, and the units are in watt per meter square. The pyrometer is an expensive piece of equipment, so handle this with care. So now, after having placed the pyrometer gives a measure of the insolation in watt per meter square, and it is a voltage equivalent that you will get. Measure for the entire day and integrate the values, and you will get HA in kilowatt hours per meter square per day. So this would mean you would get the HA for that day number N. So this HA value in kilowatt hour per meter square per day is the energy that you would have got for that particular day of the year. You could do that for every day of the year to get the value of HA over the entire year. And if you do it for many years, you will get a statistical history based on which you get an idea of the climatic conditions and the atmospheric absorptions during various times of the year and various years. Next, let us compute H0 value. We know how to do this. If we have the latitude and the day number, we can compute H0. After that, we take the ratio of HA to H0, and this will give you the KT value. So this clearness index value, remember, is for that specific value of HA. If HA has been computed for a particular day number, then KT value is valid for that particular day number. So if you want to have a KT which takes into account the historic data, then HA itself should take into account the statistical mean of all the HA values of previous years too. Then you will get the KT value, which has a much better representation on the climate and the atmospheric effects. Curve fitting for clearness index. See, generally measurement of the clearness index is for a particular place on a particular day, as we saw before by measuring HA. However, if you want to find the clearness index of a place for which measurement has not been done, then in such a case, how do we go about finding the clearness index? Curve fitting is a very nice solution. Here, even if we have measured data of few latitudes, we can make a curve fit model such that for any given latitude in the neighborhood of the place where measurements have been carried out, we can find the clearness index using a curve fit model. So that is what we will now attempt to do. Let us say we have data collected for a few of the latitudes in different parts of the country, and we will try to make a curve fit model, a Fourier curve fit model, to give you the clearness index estimate equation, and then we can find the clearness index for any latitude or any place in the neighborhood of the places where we have measured data available. Now to find the clearness index, let us first propose a model. KT is given by KT estimate. This is the KT estimate equation which we need to formulate now, plus the error. So of course, when we do an estimate, there will be an error, and therefore KT is actually deviating from the estimate equation, or the estimated value of KT will deviate from the actual measured value of KT by some error. So let us see what is the best KT estimate that we can arrive at, which will give minimum error. So one important characteristic of this clearness index is that it is periodic. So it has a periodic interval of 1 year, 365 days, and therefore we could use a Fourier series fit with a tau, the period of 2 pi n by 365, where n varies from 1 to 365, or the angle Fourier series fundamental angle can be represented in this fashion. So this would give a yearly period, and we are okay with using a Fourier curve fit method. Now let us choose this particular KTE as some function of x, like this: a1, which is a DC offset, plus a2 sine tau, plus a3 cos tau, plus a4 sine 2 tau, plus a5 cos 2 tau, plus so on. So this is the Fourier series curve fit model that we can use, which are having the fundamental and the harmonics of the fundamental. And what is x? X is contained within all these coefficient parameters, and how to find these coefficient parameters. So AI is of the form AI1 plus AI2x plus AI3x square plus so on, where x itself is a function of many things which are related to the atmospheric conditions. One is latitude, it could be water vapor, it could be beta, and so on. So our job now is to find AI. What are these coefficient values? And each coefficient value is split into a function of x of this polynomial form, and these x are a function of latitude, water vapor content, beta, the tilt angle, and so on and so forth. So this is the model that can be used to curve fit and get an estimate equation for the clearness index KTE. So let us see how we go about getting a curve fit model for the clearness index. We will use a simplistic model to understand how we go about obtaining the model, and then I will show a more accurate model using data collected from 12 cities from within the country. Let us go through a demonstration example. Let us take a very simple curve fit model and see how we go about obtaining the coefficients of the curve fit model, and then later I will expand it and extend it to a much more accurate and more exact model, and we will see how we obtain the estimate equation for the clearness index. So let us say KTE is the estimated clearness index based on the estimate equation, which is of this form: a1 plus a2 sine tau plus a3 cos tau. So it is a simple equation. I have just taken the fundamental harmonic, where tau is 2 pi n by 365. Of course, it need not necessarily be in this form. It could also be a phase shifted form. We will look at this more when we are considering the exact model. Now our job is to find out what are these coefficients. Now these coefficients ai themselves are of this form: ai1 plus ai2 into x, where x is just simply the latitude. X can be a function of latitude, water vapor, tilt angle, and so on and so forth, as we said before, other atmospheric effects. But here in this simplistic problem, we will take x as latitude, just plain latitude, and we have taken the coefficient uppercase I as ai1 plus ai2 x, just up to the first order polynomial. Now let us see how we go about obtaining the various coefficient parameters. So therefore now KTE can be written as using these format into these coefficients here. You will get a11 plus a12x plus a21 plus a22x into sine tau plus a31 plus a32x into cos tau. So this is the clearness index estimate equation, and we don't know what a11, a12, a21, a22, a31, a32 are. It is now our job to find out these coefficients and plug in these coefficients. Only then this estimate equation becomes complete, and you can use it for any other place, latitude, x and tau values. And error is given by KT. This is the measured clearness index minus the KTE, the estimated clearness index, and our job is to find these coefficients in such a way it will give the KT value such that the error will be a minimum. Now if error square will be a minimum, so let's say J is sigma EI square, which is equal to sigma KT minus KT estimate whole square. Now this is the square of the error, and we want to minimize the square of the error. So what we will do now is set del j by del a11, del j by del a12, del j by del a21, del j by del a22, del j by del a31, and del j by del a32 to 0 individually. And when you equate each to 0 individually, we will have 6 equations, 6 unknowns, and then later if you simultaneously solve that out, you will get the values of a11, 12, 21, 22, 31, 32, so on. Now we have the estimate equation here, and we know that J, the function to minimize, is KT minus KT estimate whole square. Now this is what we would like to minimize. This is the error square, so that you get the minimum square error or the least square error. So del j by del a11 is nothing but minus 2 sigma over all i's kt minus kte, and this is set equal to 0. So now we will do it for the other parameter term, del j by del a12, which is minus 2 sigma over all i's kt minus kte into x. 1, 2 has an x as a coefficient, so this you set it to 0. Likewise, if you do 2, 1, here it has the coefficient sine tau, so therefore when you differentiate, you will have sine tau I set to 0, and 2, 2, you will have kt minus kti into xi sine tau I equal to 0. That's because x sine tau. Then for the a31 and 32, you will have cos tau and x cos tau, as a multiplying factor here. We will write that down. Let me make some space. A31 is equal to minus 2 sigma kt minus kte cos tau y, setting equal to 0. Let me make more space. Del j by del a32 is minus 2 sigma over all i's kt minus kte xi cos tau y, set equal to 0. Now these are the 6 equations that you have. Kt is a measured quantity, xi, tau y are input quantities, kte, the parameters a11 to a32 are unknown. You have 6 unknowns, 6 equations you should be able to measure. You should be able to calculate. So what we do next is rearrange. You have a11 sigma 1 plus a12 xi plus a21 sine tau I, a22 sigma xi sine tau I plus a31 cos tau y plus a32 sigma xi cos tau y equal to sigma kti. So this is coming from actually this first equation. Expanding kt and kt comes to the right side, and expanding kte, you will get all those things. Likewise, if you expand the other terms, I will just run through. You can do that for all the terms. So the second term here, you will see that xi kti. Now that is what becomes xi kti, and kt estimate into xi, and that's what comes in here. You have the xi component coming in everywhere as a factor. So likewise the third term, so on. So I will just run through it, and you can work it out at your pace later on, and so on for all the 6 equations. Now these 6 equations can be expressed in matrix form, can be put in matrix form like this. So you have matrix with the component parameters, the coefficient parameters a11, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2, 6 coefficient component parameters, and they're equal to sigma kti, sigma xi kti, sigma sine tau y kti, sigma xi sine tau y kti, sigma cos tau y kti, sigma xi cos tau y kti. These are the. So this is the matrix representation. You have the 6 set of equations represented in the matrix form. This matrix here, which is shown blank, contains the coefficients of these equations, like this xi, the sine tau y, xi sine tau y, sigma cos tau y, so on, sigma sine tau y, so on. All these things will get populated here, and these values can be calculated. And here this particular column vector can be calculated because we know kti, xi, sine tau y, and the only set of unknowns will be this column vector a11, 1, 2, 2, 1, a22, a31, a32, and you have 6 unknowns and 6 equations which you can calculate easily. Now we need to look at the input data. Now this input data is needed because we need to know what are these values, what is kti, what is xi, what is sine tau y, and what are all the various elements of this coefficient array. So normally you have to get a set of input data, measured data, and you should get as many as possible so that you get very good results. So I represents the number of data, more the better. We need phi, the latitude, we need the day number n, we need to compute h naught, ha, kt, the clearness index, and you need tau, x, sine tau, cos tau. These are the values which you need if you have to compute this matrix and this matrix. And phi is something given input, n is also a given input, h naught is computed based on phi and n, ha is measured using pyrometer, which we discussed a while back, kt is computed using ha and h naught, tau is computed using n, x is computed using phi and other atmospheric parameters, likewise sine tau and cos tau are computed. Once you have all this data, you can solve for A11, A12, A21, A22, A31, A32 and so on, and obtain the values of this. And note that this is a one-time computation. You are not doing it dynamically every time. This you compute it one time using a set of data that has been measured by anybody, and using that data you have arrived at these coefficient values, which will go into the clearness index estimate equation. Now the clearness index estimate equation can now be written as A11, which we have found out, plus A12x plus A21 plus A22x into sine tau plus A31 plus A32x into cos tau. So this becomes the estimate equation, and this equation you can save it and keep it at one place or put it as a script file in a program like MATLAB or Octave, and then use it for finding out the clearness index at any latitude by substituting it within x and then computing the value through this estimate equation. And the latitude value that you use need not be the one for which the measurement data has been made available. It could be any other latitude also within the neighborhood which will fit into that geographic location, and because of the curve fit equation it will give you a very good estimate. Now if you go back and look at the steps to estimate HAT, this is what ultimately you want: the incident energy on a tilted flat plate collector at any given place with atmospheric effects, HAT. So we saw that we need to have the latitude, day number, tilt angle. You can estimate H naught, you can estimate HOT. Estimation of KT was deferred. That's what we wanted to do it last, and then we have now a method where you can estimate KT for any given latitude and day number. We will use this type of an equation, a curve fit equation, a Fourier curve fit equation. Then we find RD, which is HOT by H naught, estimate RT and calculate HAT as RT into KT into H naught. Let us now discuss a curve fit model for India. It is based on measurements taken from 12 cities and towns from various parts of the country. So the model goes like this. The estimate equation is of this form: A1 plus A2 sine tau plus A3 sine 2 tau plus A4 sine 3 tau. So we go up to the third harmonic, and then we have the cos terms also: A5 cos tau, A6 cos 2 tau plus A7 cos 3 tau. Now this is the model framework. This is a Fourier series curve fit model. We need to estimate what is A1, A2, A3, A4, A5, A6, A7 based on atmospheric parameters. So how do we find the various parameters? First, let us take tau, that is the yearly period. Instead of taking 2 pi n by 365, we shall take 2 pi n minus 80 by 365. This gives a much better lower mean square error. Then the AIs are of this form: AI1 plus AI2 x plus AI3 x square plus AI4 w plus AI5 w square. So now what is W? W is water vapor content in the vertical column above the locality. We have included that into the effects of the coefficient components of AI. And what is X? X is 5 latitude in degrees minus 35 degrees. So this set of definition give a very good accuracy of the estimated clearness index. Now, how to get the water vapor content? Of course, one can do a measurement of the water vapor content, look at meteorological sites and obtain them, but again this is a tough thing to do. We need to have it integrated into the model. Therefore, again, something like the clearness index, we make a sub Fourier series model to estimate W. So W is of the form G1 plus G2 sine tau, G3 sine 2 tau, G4 sine 3 tau plus G5 cos tau, G6 cos 2 tau plus G7 cos 3 tau, where GIs are of the form GI1 plus GI2 x plus GI3 x square, where x is the latitude as defined here. Now this would give you the entire model. So first what you do, given the latitude, we estimate these this portion, that is the water vapor content, because you need to know the latitude and the day number to find tau. Then water vapor content can be estimated from this estimate equation. Then this can be plugged in here to define the AIs, and then that can be used to estimate the clearness index by plugging it in here. So this is the model that we have used to find the clearness index at any place within the country. It is a reasonably good model, accurate within 15%, and which is sufficient for design, because we are anyway being conservative when we are designing the photovoltaic panels. So this model, we can put it as a script file within the Octave or MATLAB and execute it to obtain KTE.